Have you ever stopped to think that, at this very moment, thousands of tons of steel are floating right over your head at 30,000 feet? The secret to why a plane doesn't fall isn't just about the raw power of the engines, but an invisible dance between the air and the metal itself. At 30,000 feet, the air is much more than just empty space. It acts as a physical medium with its own weight and resistance. Imagine the sky as a vast, invisible ocean of molecules. For an aircraft to stay aloft, it must constantly displace thousands of tons of this fluid every single second. This resistance, which we call drag, is the primary force engineers must fight, but ironically, it's also what makes flight possible. Without the physical body of the air to push against, the wings would have no support, and the control surfaces would have no way to grip the sky and steer the massive vessel. Look closely at the shape of a wing. It isn't flat. It's curved on the top and straight on the bottom, creating what we call an airfoil. This specific geometry forces the air to behave in a very special way once the aircraft gains speed down the runway. The specific curvature of the airfoil isn't just about pressure. It relies on a phenomenon called the Coanda Effect. This is the tendency of a fluid jet to stay attached to a convex surface. As the air hits the leading edge of the wing, it doesn't just bounce off. It sticks to the metal, following the curve all the way to the back. This sticky flow ensures that the air is directed exactly where the engineers want it, preventing the chaotic turbulence that would occur if the air detached from the wing. This smooth, attached flow is the difference between a stable cruise and a catastrophic stall. As the air moves faster over the curved top surface, the pressure there drops drastically, creating a sort of partial vacuum that pulls the wing upward. At the same time, the slower, denser air underneath pushes the structure with a massive force called lift. When we look at pressure from a molecular level, the bottom of the wing is experiencing a constant bombardment. Trillions of air molecules are striking the lower surface, transferring their momentum directly into the metal skin of the aircraft. Because the wing is angled slightly upward, what we call the angle of attack, it acts like a giant shield deflecting a continuous storm of particles downward. This downward deflection is the physical action that results in the reaction of lift, effectively allowing the airplane to stand on a pillar of deflected air. But lift alone isn't magic. For it to exist, the plane must overcome air resistance, an invisible barrier that tries to hold the aircraft back at all costs. This is where the engines come in, true powerhouses that swallow tons of air every second to generate the necessary thrust. Inside the core of the engine, the air undergoes a radical transformation. It's not just sucked in. It is violently squeezed by successive stages of spinning titanium blades. By the time the air reaches the combustion chamber, it has been compressed to a fraction of its original volume, causing its temperature to skyrocket to hundreds of degrees just from the pressure alone. This high-energy, high-density air is the perfect primer for the fuel. It ensures that every drop of kerosene is used with maximum efficiency, creating the concentrated power needed to push a 500-ton machine through the sound barrier. Inside a turbine, air is compressed to extreme pressures before being mixed with fuel and detonated in a controlled explosion. This jet of gas expelled at incredibly high speeds backward is what propels the metal giant forward, allowing the wings to do their job. The temperatures generated during this process are so extreme they would easily melt the very metal the engine is made of. To prevent this, engineers designed microscopic cooling holes in the turbine blades. A thin layer of cool air is bled from the compressor and forced out through these holes, creating a protective thermal film over the metal. It's a literal shield of air that protects the engine from its own fire. This allows the turbine to operate at temperatures higher than its own melting point, a feat of materials science that makes modern long-haul travel possible. If you could actually see the air, you would notice it behaves like a viscous fluid, almost as if the plane were swimming in a pool of invisible density. The faster it moves, the solid the air becomes, serving as a physical support to keep the fuselage stable. This fluid behavior of air is why the surface of the airplane must be kept incredibly clean and smooth. Even a thin layer of frost or a minor dent can disrupt the boundary layer, the thin layer of air directly touching the wings. When this layer becomes turbulent, it creates parasite drag, making the air act more like sandpaper than water. By maintaining a laminar flow, where layers of air slide perfectly over each other, the aircraft can maintain its stability and speed with minimal energy. It is the difference between slicing through the sky and fighting every inch of the way. The balance is so precise that four forces are constantly fighting each other. Weight pulls down, lift pulls up, thrust pushes forward, and drag pulls back. As long as these forces remain in harmony, the plane is, technically, a structure perfectly supported in the sky. These four forces are in a constant, dynamic tug-of-war that changes with every move the pilot makes. When the plane climbs, thrust must overcome not just drag, but also a portion of the weight. This is why you feel a push against your seat during takeoff. It's the physical manifestation of excess thrust winning the battle against inertia. Engineers use complex flight control laws to ensure that no matter how much these forces shift, the aircraft remains within its flight envelope, a mathematical safety zone where the metal and the laws of physics are in perfect alignment. A common mistake in intuition is thinking that if the engines stop, the plane falls like a stone. But engineering foresaw this with the concept of gliding. Even without power, the angle of the wings and the accumulated speed allow the plane to slide through the air, traveling miles without spending a single drop of fuel. The secret to this incredible gliding ability is the lift-to-drag ratio. Modern airliners are designed to be so slippery that they can travel nearly 20 miles forward for every single mile they drop in altitude. This efficiency isn't just a safety feature. It's what allows the plane to cruise economically. Pilots are trained to manage this energy carefully, turning the aircraft's massive weight and height into a battery of potential energy. In an emergency, this energy is spent second by second to keep the air flowing over the wings, proving that speed is the ultimate insurance policy in the sky. Notice the wingtips, which often have small folds called winglets. They aren't decorative, they are there to tame invisible hurricanes. Without them, air would escape through the ends, creating vortices that steal energy and dangerously increase fuel consumption. The vortices that winglets combat are a form of induced drag, a direct byproduct of creating lift. As the high-pressure air curls over the wingtip, it creates a downward spiral of air that actually pushes the back of the wing down. This makes the wing think it is flying at a steeper angle than it really is, forcing the engines to work harder. By breaking up these spirals, winglets effectively trick the physics of the wing into being more efficient. It is a brilliant example of how a small geometric change can outsmart a massive physical force. Behind every curve of the fuselage, there is a mathematical decision to ensure the center of gravity is always ahead of the center of pressure. This makes the nose of the plane naturally tend to dip if speed drops, forcing it to gain acceleration and recover lift automatically. This self-correcting nature is known as static stability. Think of it like a marble at the bottom of a bowl. If you push it, it naturally rolls back to the center. If a gust of wind knocks the plane's nose up, the decrease in speed immediately reduces the lift on the tail, causing the nose to drop back to its original position. This inherent desire of the machine to return to level flight is what makes long-haul flying manageable. The plane isn't just a vehicle being steered. It is a balanced system that uses its own geometry to fight against chaos. And what happens if the air becomes thin or turbulent? Tiny sensors called pitot tubes measure external pressure every millisecond, sending data to the onboard computers. These systems adjust small moving surfaces on the wings to ensure the flight stays smooth, even in extreme conditions. Today, this delicate dance is assisted by fly-by-wire technology. Instead of cables and pulleys, your inputs travel as electrical signals to computers that interpret the air's condition. These computers are so fast they can sense a stall before the pilot even feels a vibration. They can move the wing's trailing edge in tiny increments, thousands of times per flight, to counteract the invisible shifts in air density. It is a seamless partnership between the rigid laws of fluid dynamics and the lightning-fast processing of modern silicon, creating a flight experience that is smoother than any mechanical system could ever achieve. The truth is that a cruising airplane is one of the most stable machines ever created by humanity, designed to physically self-correct. Flying isn't about defying the laws of nature, but understanding them so deeply that the sky becomes the safest place to be. Every critical system on board, from the hydraulics that move the flaps to the electrical grids that power the cockpit, is doubled or even tripled. This philosophy of redundancy ensures that even if one law of mechanics fails, another is there to catch it. We have mastered the sky not by ignoring its dangers, but by engineering a world where every possible failure has a pre-calculated solution. This is why, despite the staggering complexity and the sheer weight of the machines, the sky remains a place of profound logic and safety. Thanks for watching. We are Exposed Engineering. Subscribe for more.